Hey all, this is Mr. Yeager with Honors Chemistry. I'm just adding a little bit of extra information to our talk on radiation and basically understanding nuclear reactions. Okay, so in the other video that you watched, introducing all the radiation types, we talked about basically the idea of transmutation of the nucleus. Again, transmutation is just another word for saying a new element's going to be created. New element created. All right. So transmutation, radioactive decay, nuclear reactions, they all form a new atom because we're changing the protons and neutrons in it. So there's three things I just need to quickly add to what I had in my prior video about nuclear stability. It goes back to the idea of like, why would radiation be released? Why would the atom even want to change what it is? Okay, and it goes back to even the idea of what's in the nucleus. Again, we have protons and neutrons in the nucleus itself. Okay, and we know the nucleus has a positive charge because of the protons. The thing is, protons, since they are positive and positive repel each other. Okay, the idea that they're, how is this nucleus holding together if we have all these positive charges that are trying to push it apart? Okay, well, one of the reasons that it doesn't really fall apart, I mean, there's a few reasons with it, is because, one, to start off simply, there's neutrons. Okay, and this is again why we knew there had to be something else in the nucleus after we discovered the proton. We didn't discover the neutron until about 21 years after the proton, because it had no charge. There was nothing that we really could see why it was happening in there. It wouldn't obviously repel. All right, these neutrons are not repelled by the positive charge. Neutral objects are not repelled or attracted. So then we also have another question. Why do even the neutrons stay together? Like, why do all of these things stay together? And so we have something that's there called the strong force. And that seems like a really, really silly name. Like I'm just saying, there's something strong holding it together. No, this is a legitimate name of the force that's holding the nucleus together. It's called the strong force. So the strong force is basically an attractive force between the protons and the neutrons, and then neutrons. Okay? So there's this force that's present between them that makes them want to stay together, all right, based on what they are, really, in the end. It actually gets farther down to smaller particles called quarks, and I think there's one called leptons and things like that, where they're actually, based on their arrangement, are attracted to each other, and it just happens that when they are arranged, they're forming these protons and neutrons as well. So we have a strong force holding the atom together, holding the nucleus together. Okay, this is different from the electrons that are attracted to the protons and vice versa. That is an electromagnetic force, and we'll talk about that more later. Okay, but that's a different type of force that's occurring between the two other particles there. Okay, that the protons keeping those electrons within the atom itself. So when this strong force is not strong enough, okay, that's where the atom can't hold itself together, the nucleus. I keep saying atom, sorry, I'm focusing on the nucleus. And the atom can't contain that energy, and it is released. Okay, it is released in the end. So that's one of the main factors of nuclear stability, is the fact that this strong force holds it together. One of the other things that it depends on is the proton-neutron ratio. All right, and this is not something you got to calculate. I'm not saying there's some special number you need to remember for the proton-neutron ratio. We just got to remember this statement that there's a proton-neutron ratio that each individual element's trying to achieve based on its makeup. Okay, and this is where we get into the idea of isotopes, and obviously half-life you're going to see in a little bit. But my quick little example, and again, I don't have the exact number, so I'm making up these numbers going along here. Okay. We're going to learn that half-life, how long the half-life is, tells us how stable the nucleus is. The longer the half-life, the more stable it is. So again, I'm making up these numbers, and I think I might have them backwards, but let's just use them for what they are. I'm going to say U-238 can last 1 million years. Okay? In other words, it takes 1 million years for half of the substance to decay, which means it's very, very stable. But if I go to U-235, all of a sudden it's going to decay in 50 minutes. That's a pretty stinking significant difference between the two. And again, these numbers I'm making up. I did not look them up. I'm just giving a general example. I should just make up an atom here. But it's the same idea I'm going with. All right. What happens here is both of these are isotopes. So they both have 92 protons. And the only difference between them is the number of neutrons. Okay. If I do this math right, this should be what? 246 for neutrons for 238. And then 243 for U-235. But while it seems insignificant, this change of 3 neutrons causes the atom to completely be destabilized. The ratio of those protons and neutrons, the neutrons being able to keep all the protons apart, is just not good enough anymore, and it's able to break apart. Okay? Just to mention, there is another force that actually helps with radioactive decay. This one we're not going to really test on too much, okay? But I just want to mention it. There is another force out there called the weak force, and basically this is a force that helps encourage radioactive decay, okay? Like when this weak force comes into play. It obviously has a relationship with the strong force where these two are competing against each other, and the strong force is generally stronger than the weak force. But a weak force is basically occurring between the particles in the nucleus that's trying to actually cause them to break apart. Okay? So those are a couple of things I just wanted to share, and have a good one.